So, Taylor and Maclaurin series. So, in the following theorem, if A happens to equal 0, then the whole thing turns magically into a Maclaurin series. There's no actual difference between Taylor and Maclaurin, it's just where it's centered. So, what is the formula actually saying? It's saying that just what we did in the last video, which is if you want to approximate some function, some arbitrary function, as long as you can take any arbitrary number of derivatives of it, and it's totally fine if the derivatives go to 0 as long as they don't do something bad. Okay, so you just calculate all these derivatives and divide by n factorial and then pop on this term and you sum them all up, and the crazy thing is we're saying this works. We're saying that for one thing this doesn't work unless the terms keep getting smaller and smaller regardless of what you pick for x. So think about what's happening. Okay, this is only going to work. Let's just pretend a is 0 because it doesn't much matter. But you have some constant. Let's pretend that the derivative, let's just make it 1. Make them all 1. So essentially what you're looking at is something of this pattern. You're looking at the limit as n goes to infinity of these pieces. And what's happening? So you plant x down wherever you want, and eventually, so you fix x, and n grows. So as n is growing, so initially this thing is top heavy. Initially you assume that, x to the 17 is going to be larger than whatever's on the bottom. But eventually when the x and the n are the same size, then it's going to kind of stabilize. And then eventually n's going to get bigger and bigger and bigger, and the whole thing's going to collapse into 0. So that's essentially what's going on. So we'll talk about that more. But let's go on to our next. Let's go on to a small example. If you have 3x squared minus 2x plus 7, how could you write that as a Taylor series about 4? Well, you have to start taking derivatives. Okay, f of 4 is 3 times 4 squared minus 2 times 4 plus 7. And we'll calculate that in a second. And then you have to know the derivative of f, 6x minus 2. So f prime of 4 is 6 times 4 minus 2. We'll get that later. Second derivative, 6. So f double prime of 4 is 6. And f triple prime, and all the remaining derivatives are 0. Okay. So, okay, this first thing evaluates to 47. The second thing evaluates to 22. You'll just have to take my word for that. Okay, so all this together tells us that f is approximately equal to 47 plus 22 is the coefficient in front of x minus 4, and then plus 6 over 2 is the coefficient on x minus 4 squared. So if you remember in the formula, you have to divide by n factorial. We talked about that in the last video too, why we have to do that. Okay, so that's why this is the first term in which the divide by shows up. The next term it'll be divide by 6, because you go 2 factorial, 3 factorial, 4 factorial. Okay, so this is just the first time this shows up. Okay, so f, but it's not approximate, it's actually equal to, because since we have just a parabola, we're just shifting this parabola. Okay, so what does this really mean? Let me draw a picture and explain what it's actually saying. So I'm going to try to squeeze all this stuff onto this picture here, to this screen. There we go. So I'm going to just try to draw what does this function really look like. Okay, so we know that f of 0 is 7, so we've got a point there. I don't know where the vertex is, but I'm just going to guess that it's somewhere around here. Okay, let's just pretend. Maybe it is, maybe it's not. Okay, but at x equals 0, what this is saying is f is equal to 7, f prime is equal to negative 2. So I'm getting it from this piece right here. So I got the plus 7, I got the minus 2, and the second derivative is just going to be 6. Okay, so it's just this guy times n factorial. However, I could take another point, let's say up here, at x equals 4, f is equal to 47, f prime is equal to 22, and f double prime is equal to 6. And because what I have is a parabola, all other derivatives are going to equal to 0 all the way down. So all the rest of the derivatives are 0. So what we're actually saying is, for any polynomial, this is true, that if you just take any point on your polynomial, and then you just say what's the value at that x value, so what's the f value, what's the first derivative, what's the second derivative, the third derivative, and you list all your derivatives until you get to 0, you've actually uniquely determined your entire polynomial. And that's just crazy. It's just crazy. You're like just stacking up all the information at that point, and you're saying that's enough to uniquely determine the curve's behavior everywhere. And we had some discussion about this in class. How, 2 points determine a line, but instead of having 2 points, you could instead have 1 point and 1 slope. Or 3 points determine a parabola, but instead of having 3 separate points, you could just say 1 point and stack up all the information on that 1 point. So you have to have the same amount of information, but you could spread it all over the curve, or you could stack it up in little packets, or you could put some information, 2 little packets of information together and another 2 little packets somewhere else. There's no end to all the different ways in which you can distribute that information. But specifically with Taylor series, Maclaurin series, what we're actually saying is we're stacking up all the information at 1 point. And we're furthermore saying that you don't have to have a polynomial to start with. You can start with any function you want, start stacking up information, and you just have to have an infinite amount of information. That's just kind of mind-blowing. And that will allow you to fully recover the entire curve. Now you may think, well, how does this work? Okay, so I want you to think this way. You have some kind of function, I don't know, okay? And I'm just going to say, like, pick a point, like here. So the first thing I would do is approximate this with some kind of a line, okay? So I would call this like T1. And then the next thing I do is approximate it with some kind of parabola. I'd call that T2, Taylor 2. And the next thing I do is I'd, find some kind of cubic. So maybe it would look like this. I don't know. I'm just guessing here. But what happens is, as this polynomial, as this subscript gets higher and higher and higher, maybe like something like this, this might be where T15 is. Okay, they just, as you crank up that subscript, then the next approximating polynomial is just going to hug the curve tighter and tighter and tighter, and for longer and longer and longer. And that's what happens. And so in class I use the example of you're shrink wrapping something in plastic. Okay, so you start at the center of wherever you want to shrink wrap something, and you kind of run the hairdryer over like this little, I need a little curve. I need to point with something here, an eraser. There we go. And this point. Okay, so I'm going to just run the hairdryer right here, and then slowly make my way out in either direction as my approximating polynomial hugs the curve more and more tightly. Okay? So let's give a couple examples. Right. Find Maclaurin series But just Taylor at x equals 0, no big deal. So it's just a shorthand way of saying find the Taylor series about x equals 0. I don't know that it's really that much shorter though. Okay. So the neat thing about e to the x is any derivative is just itself. So that's great because if you evaluate it at 0, it's always 1. That's awesome. So why is this awesome? Because you get this sort of thing going on. Okay, you just go ahead and run this formula and no big deal, right? N equals 0 to infinity, x to the n over n factorial. But don't worry, you're not dividing by 0 because 0 factorial is actually equal to 1, so you are safe. You can totally do that. And e is equal to f of 1. And then you get this nice little expansion for e. You should know that. All right, and that's pretty straightforward. Okay, next example. You know what? I'm going to just save writing a little bit. There we go. Find the Maclaurin series for f is sine of x. Now, if f is sine, f prime is cosine, f double prime is minus sine, f triple prime is minus cosine, and they're all going to be evaluated at 0. So f of 0 and f double prime of 0 are both going to be 0. F prime of 0 is 1. F double triple prime of 0 is negative 1. Okay, so half the terms wipe out completely, and the other remaining terms toggle plus and minus 1. Put all this together, and you're just going to say sine of x is approximately, okay, so the constant terms wipes out, so we start with x minus x cubed over 3 factorial. You're just going to have odd terms, and the signs are going to alternate. Okay. No sweat. Same thing going to happen for cosine, but we're just going to get all the missing pieces that we didn't have for sine of x. So let me just say what happens here is we just chop these guys, slide them all down like that. I'm being a little bit lazy here on purpose. Okay. Right, I gotta get rid of some of these prime symbols. Okay. Just being a little bit silly here. But now we have cosine of x is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, etc. So it's exactly the same process. There you go. Okay, so the whole battery of things to keep track of. You should know e to the x, e to the minus x. You should be able to go e to the x plus e to the minus x now. This is actually cosh, or hyperbolic cosine. E to the x minus e to the minus x over 2 is sinh, or hyperbolic sine. And you can put all these pieces together and demonstrate e to the ix plus e to the minus ix over 2 is actually equal to cosine of x. And you can prove all these identities just using the fact that you now have Taylor and Maclaurin series at your disposal. Wow, you may prove this now. You can prove this using Maclaurin. Woo! Great. Holy have this guy too, e to the x minus e to the minus x over 2I. Guess what that equals? Sine of x. Awesome. I'm going to let you guys do out all that algebra if you want. This is a video and I'm saving a little bit of time, but you guys can do that yourself. And cosine of x plus I sine of x equals e to the ix. That's right. Cool, cool, cool. And of course we have the famous formula. It's very, very similar to that, only we got it with the, we have to put the r in there. R cosine theta. See, Euler would be proud of us. Or not, I don't know. Yay! How cool is that? While we're giving definitions and stuff. The nth Taylor, oh yeah, I'm going to call this K. I'm going to use the N. No, I'm going to use the N here. There we go. Equals sum K equals 0 to N. Put all these pieces together. Where have we seen this before? Okay, this is the kth degree Taylor approximating polynomial at A. The quote means I'd like to put italics, but my handwriting doesn't do italics. Okay, so again, this only makes sense if the following is true, which it's true. Limit as n goes to infinity of x to the n over n factorial equals 0 for all x in the real domain. And this is true. And let me convince you that it's true by using an example. So this is not a proof, but this is an example, and the underlying rule will be true even though I'm just picking an example. So pick x equal to 1,000. So 1,000 to the power of 3 over 3 factorial. Okay, this guy looks like the 1,000 wins, right? So the 1,000 cubed is definitely much bigger than 6. However, what about if you then hike up that exponent to, like, say 5,000, okay, and then you take 5,000 factorial, now the 5,000 factorial is obviously going to win, right? Another way to think about this, when you first start building this 1,000 over 1, and then it's 1,000 over 2, 1,000 over 3, times 1,000 over 4, and for a long time the thousands are building, so this whole thing keeps building. So just this piece is a sub 1, this piece altogether is a sub 5, right? So a sub n plus 1 is a sub n times 1,000 over n plus 1, okay? So you just keep building, building, building. But what's going to happen after you get to, you know, a 1,000 is a 999 times, now what? You always multiply by 1,000, but now you're actually going to divide by 1,000. So a 1,000 and a 999 are going to be the same. And then from now on, it's going to start decreasing, right? So it's going to be actually the same as what we had before, but I'll just write a 1,000. I could have written 999 if I'd wanted to. Subscripts are a mess. Okay. So you have a 1,000 times, now what are we going to do? We're going to now do 1,000 over 1,001. And you're like, well, it's only going to decrease a little bit. Sure. But then when you get to A 5,000, it's going to be like A 4999, and guess what the multiplier is going to be now? Now you're going to be decreasing by a factor of 5 each time, and the factor by which you're decreasing is decreasing. So that thing is just going to squash down faster and faster and faster and faster. Okay, so eventually that thing is just going to go to nothing. Nothing, nothing, nothing. So the whole point is that this statement actually is true. Okay? Was there anything else I wanted to say? I wanted to mention that the Maclaurin series for this guy, we did this in class and we showed that it was a combinatorics problem, and this is right in your textbook and ends up looking this way. People said they were pretty comfortable with this notation, but just in case you haven't seen it before, I do want to mention that this piece is the combination of k things taken n at a time, and there's many ways of writing that, so I just want to make sure you're familiar with all the different ways of writing. Combination of k things taken n at a time, which is sometimes written like that. Okay? There you go. So all those different forms of writing that combination, they're all the same. Okay? So then we can rewrite this formula and what else did I want to say? There was a book example that we're definitely skipping. The book example that we're not going to talk about is this one. We're not going to talk about that expansion, but arctan of x, that one is fair game for testing or whatnot. Okay? And we use the fact that derivative of arctan is what? I don't expect you to memorize this, but I can tell you this fact on an exam, and then once I tell you, you should be able to take it from there. Okay? And one last little thing, just because it's fun, is you can take advantage of these expansions to simplify certain tasks. Okay? So you could use L'Hopital's rule repeatedly, and that's fine, but I can make things that are even more complicated, more interesting. And I could just say, hey, wait a minute, e to the x is 1 plus x squared over 2 plus x cubed over 6, blah, blah, blah. Okay? And so then if I subtract out the 1, I subtract out the x, what I'm left with is x squared over 2 plus x cubed over 6 plus blah, 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 all over x squared. And then this becomes, so this is a limit as x goes to 0. And these things they fall into the category of easier to do than to talk about doing, right? Okay, and then these guys all cancel out, so the limit's 1/2. So even though I just wrote a lot, and you're like, well, you know what, you could have just used L'Hopital's rule. That's true. But the point is, once you get used to dealing with these series, you'll just look at e to the x and see that expansion and say, oh, look. These pieces over here are just, these pieces are right from e to the x. So you just, in your mind, you immediately, instinctively think of this and say, well, you know, I'm just going to divide off the x squared here and I'm going to get 1/2. So the point is, this complicated problem, you can actually do in your head because you'll do this arithmetic in your head. But it's a little harder to do L'Hopital's rule twice on 2 different functions in your head. So, anyway, hope you had fun with that, and make sure you tell me if you have any questions, and I will see you in class. Have fun.